Welcome to section 3.2, Properties of Determinants. There are some properties of determinants that we'll want to discuss so that we can find another method in which we're able to find the determinant of a square matrix. It is a lot easier to calculate a determinant when the matrix is triangular. So remember, that means you have some zeros down here. Or when there are a lot of zeros. So if there are a lot of zeros in a specific row or column. Now, the new part that we'll see today is that we can use our elementary row operations to transform a matrix into one of these characteristics. So if it is not one of these already, we can alter the matrix so that it is easier to calculate the determinant. Now, depending on which of the elementary row operation we use, it could have some sort of effect on how we calculate the determinant. So there are some different rules that we will need to keep in mind. So let's look at a simple 2 by 2 matrix and kind of analyze what happens. So I have this 2 by 2 matrix, and let's go ahead and find the determinant of this. So if I want to find the determinant of matrix A, I take 3 times 6, which is 18, minus 4 times 5, which is 20. So this determinant is -2. Okay, well, let's perform one of the elementary row operations and see how that compares to the actual determinant of A. Now, let me remind you of the 3 elementary row operations. There is replacement, where you multiply one row by something and add it to another. So replacement. There's swap, which is also referred to as interchange. So that's just flipping the locations of a couple different rows. And then there's also the scalar, the multiplying. Okay, so those are the 3 elementary row operations. Let's perform one of them on this 2 by 2 matrix and see what happens. Let's go ahead and swap these 2 rows. So we're going to interchange. And let's just call this matrix B just for simplicity's sake. So the second row becomes the first, and the first row becomes the second. And let's go ahead and find the determinant of this. So that's 20 minus 18, which is a +2. So let's compare these. How do they compare? Well, the sign is different, right? Okay, note to self. Let's try one more example. Let's try a scalar. Let's take 3 times row 1, and let's call this matrix C. So if I take 3 times this first row, I get 3 times 3, which is 9, and 3 times 4, which is 12. All right, let's find the determinant of this row, or I'm sorry, this matrix. Here I take, this should be 6, sorry. I take 9 times 6, which is 54, minus 60, which gives me a -6. Okay, well, how does the determinant of this compare? Well, I multiply this original determinant by 3, which happens to be what our scalar multiple was. Interesting. So these observations lead us to the next theorem for properties of determinants. So this theorem is going to be widely used in this section. It's pretty important. So basically, if we use replacement, so if I multiply one row by something and add it to another, which is a lot of what we did before, you know, when I would write 2 times row 1 plus row 2 becomes the new row 2, right? That's replacement, okay? If that's the case, then the determinants of the two matrices are equal to one another. Okay, well, if I swap or interchange, remember how those were opposite signs? Well, it's basically the negation. And then I illustrated this one also. If I multiply, then whatever that scalar is, it's going to be multiplied by the determinant as well. Okay, so now we're going to use this theorem and we are going to see an alternative method of finding the determinant, and that's by using row operations. Here is our first example. So the strategy here is to reduce this matrix to echelon form and then use the fact that the determinant of a triangular matrix is the product of the diagonal. So basically you want to try to get a diagonal matrix so that there are the zeros down in the lower triangular area. Okay, so what I mean is we want to make these 0. Okay, so let's proceed. Determinant A, the determinant of A is found by the following. Let's go ahead and make this 0 first. So I'll make that 0 by multiplying the first row by 2 and adding it to the second row. So the first row remains the same. When I multiply the first row by 2 and add it to the second row, I get the following. And then I'm just going to keep that third row as is. Okay, now remember with row replacement, it does not change the determinant, so I can proceed. All right, well now I'm going to do the same thing, but I want this entry to become 0. So I'm simply going to add row 1 and replace it. So it's just those same elementary row operations that we dealt with before. So when I do that, I have this. Now, one of the operations that we didn't use very frequently was interchanging the rows. Now, if I look at this, I do have these zeros here. And if I swap these rows, or if I interchange, then I'll have that triangular matrix. And remember, according to that theorem on the previous slide, anytime I interchange, then I need to negate the determinant. Okay, so when I interchange, I end up with a negative. So the third row becomes the second. Oops, this should be a -5. Okay. All right, well now I have my triangular matrix. And I mentioned before that if you have this, then you can take the product of these diagonal entries. So the determinant is this -1 times 1 times 3 times -5. And when I multiply that, I get 15 for the determinant. Not so bad, right? So in this example, we had some row replacement. Remember, with row replacement, you do not need to do anything with the determinant. But if you interchange the rows, or if you multiply the rows by something, then you do need to take that into account when calculating the determinant. So let's look at another example. Okay, so in this one, we want to, again, use elementary row operations to find the determinant. Now, this is going to be an alternative method. Okay, so this is a little bit different. So if you look in the first row, these all have a 2 in common. Now, notice this first entry is not 1. We need that to be a 1. So what we're going to do is we're going to factor out a 2 from row 1. So when I calculate my determinant of A, I'm going to call this matrix A. When I calculate that determinant, I need to multiply by 2. Okay, so I'm basically taking out that GCF. And then I'll just rewrite the rest. Okay, well, now I need some zeros, so let's start with these here. I'm going to make those 0 by using row replacement. And since I'm using row replacement, there's no change on the determinant. So row 1 remains. To get row 2, I'm going to multiply row 1 by -3 and add it to row 2, giving me that. Same type of thing with row 3. In order to get the new row 3, I'm going to multiply row 1 by -6 in order to get a 0 here. And the other entries are as follows. Now, you can play with this a little bit, and you'll find that sometimes, depending on your choices, it takes a lot more time to get this into a triangular matrix. So you just need to kind of play with it a little bit. Okay, but remember that interchanging is going to be helpful. So I want this to be 0, but it's a little complicated to get that to be 0. And there are a couple different ways you can do this. Okay, so just keep that in mind. I'm just giving you one illustration. So I'm going to interchange, and remember, when I interchange, I need to negate the determinant. So that now becomes a -2. Row 1 remains the same, but now I've changed the location of these just for simplicity's sake. So now what I'm going to do is I am going to factor out a -2 from row 2. So that's going to change. So now I'm going to have another -2. And I'm kind of doing it this way for illustration purposes also, just so you can see my work and what happens. So when I factor out that -2 from that second row, now I have this. And I'm going to do the same thing with this third row. I'm going to factor out -4. So I have -2 times -2 times -4. Okay, so we're getting a little bit closer, but now I want this entry to be a 0. So if I want that entry to be a 0, what I'm going to do is use row replacement. I'm going to multiply row 2 by -1 and add that to row 3. Since I'm using row replacement, I don't need to do anything fancy to this piece here. But my third row becomes the following. Since I have a triangular matrix, I can multiply these diagonals and then multiply this. This here is a -16 times that diagonal, the product of the diagonal, which is -4, and this gives me a determinant of 64. So this is an example of using elementary row operations to find the determinant. Okay, well, here's an even bigger matrix. So here we have a 4x4 matrix, and we're going to do the same type of thing. Now, I have to admit that, so this problem is in the book, and I wanted to try a different method. So I went ahead and I think I interchanged first. So I flip-flopped these, and that's something you can certainly do, but it went on and on and on and on. And then I looked at how they did it, and their method was much shorter. So like I mentioned a few moments ago, there are multiple ways in which you can solve these problems, but some are shorter than others. So let's take a look at how we can solve this. Now, remember, you want this first entry to be 1. And if I look at this first row, I notice that they're all even, so I can factor out a 2. And if I factor out a 2, then that first entry becomes 1. So let's go ahead and do that. So this ends up being the following. And then everything else remains the same. Okay, so now I need to get these 3 entries to be 0. And the way I'm going to do that is by row replacement. So the same things that we've been doing. Okay, so because I'm using row replacement, that does not alter my determinant at all. Oh, one important thing, I'm so sorry. I need a 2 here because I factored out that 2. But with row replacement, I don't need that, so this becomes the following. Row 1 remains the same. But with that row replacement, the next 3 rows are as follows. I'm sorry I don't have any nice music playing for you in the background. Instead, you get to hear the clicking of my pen. Okay. So we're getting a lot closer to my echelon form. I'm going to make this 0 by using row replacement. I'm going to multiply row 2 by 4 and add it to row 3. To get this. And then row 4 remains the same. Okay, so all I need, there's a squirrel taunting my dog today. Okay, so all I need is this to become a 0, which is doable, but I need to use row 3. Okay, I'm not multiplying by 2 Instead, I'm going to multiply by a negative 1/2 times row 3 plus row 4, and that will become my new row 4. So this becomes 2 times the following. Okay, so this fourth row is 0, 0, 0, 1. So once you have these zeros here, then remember you find the product of the diagonal. Don't forget this 2 out here. So the determinant of matrix A is calculated by taking 2 times 1 times 3 times -6 times 1, which gives me a negative 36 for my determinant. So again, this illustrates another way of using elementary row operations in order to calculate the determinant. So here, there are some other theorems in this section, and a lot of them we've talked about before. For the most part, they are pretty straightforward. Remember, a square matrix is invertible if and only if the determinant does not equal 0. The transpose of matrix A, the determinant of that is equal to the determinant of matrix A. And then we have this theorem as well. That concludes section 3.2.